And I know there's a bunch of other people on the team on the call, so I imagine he can delegate some of the questions to his people too. So with that, Chad, take it away.
All right. Well, thank you, Tom, for the introductions, and thanks to Debbie for setting this all up, and thanks to the North Shore Tech Council for hosting. See if I can get so as Tom said, I'm the Vice President of Research and Development at Encycle. Today we're going to be talking specifically about our work on sort of redefining the critical mineral supply chain. To start off, I can sort of give you sort of the origin story of how Encycle began. So as Tom stated, I developed the original technology, the sort of electrochemical filter, when I was faculty at Harvard. And really we did a lot of like sort of the fundamental research there, looking into the technology, the synergisms, et cetera, with sort of a focus on water treatment applications. And so then it was probably around 2013 when I was invited to give a seminar at a symposium that was hosted by Megan O'Connor, our CEO's PhD advisor at the time. Desiree Plata was also one of our co-founders. And the talk that I gave was on sort of the removal of metals from wastewaters, which was sort of serendipitous because at the time Megan had just started her PhD and was more thinking on the other side of not metals as waste, but metals as a valued product and the importance of their recycling. So after my talk, Megan and I started chatting, and then eventually, she asked if she could work on that project as part of her PhD. She was really taking a more holistic view of metal recycling as, as a circular process. I want to get into tech a little bit as part of it, and so I agreed. It was on her PhD committee. And so she really took the technology and pivoted towards more metal recycling, which as an application was definitely more viable than water treatment, just in terms of economics. And then so when Megan received her PhD in 2017, that's when the company started. And shortly thereafter, I joined full-time when I left Harvard. And so that was just a few years ago, and you can see how much even we've grown from then, from just the few co-founders. Today now I think we're up to about 8 full-time employees, and looking to expand even further. So yeah, so it's a nice evolution from just a fundamental research project to now being a rapidly evolving company in the metal market. So yeah, so getting on to more specifically what I'm going to discuss today is the redefining of the critical mineral supply chain. And really sort of we have to discuss first what is a critical mineral or a critical metal in this case. And so, really from our perspective, a lot of these critical metals today are metals that really haven't been used until the last couple of decades. We'll focus specifically on the rare earths, which are found in permanent magnets. And these permanent magnets are vital towards electric vehicle motors and wind turbines, as well as the metals such as cobalt, which are found to have importance in lithium-ion batteries and thus electric vehicles. And so with the rapidly growing clean economy, one of the issues is that the sort of infrastructure sort of to mine and refine and acquire these commodities for the clean economy has not been able to keep up. So there is a short supply just in general over the globe. So we recognize this again with the rare earths. Our focus there is really on neodymium and then the cobalt for the lithium-ion batteries. And on top of this, in terms of just being critical minerals, if we think about it specifically for the United States or North America, we are predominantly depending upon foreign supply chains for these metals, for these sort of this clean economy. So specifically, one we can consider is cobalt. And in the case of cobalt, the majority of cobalt is mined in the Democratic Republic of the Congo, which itself has sort of internal political instabilities. I don't know if you keep up on the news, but it was within the past couple of months, a Italian diplomat was killed there in a drive-by shooting. And so there's some really instability in terms of, is it going to be sustainable there? It's going to fall apart. And then once they are mined in the DRC, the minerals are sent to China, where over 90% of the cobalt is refined. And obviously there are some issues, depending on China, for a supply chain of a mineral that is critical for clean energy, especially if we're going to start continuing these trade war type relationships. Then again, getting back to just the supply deficit as a whole, you can see here, this is a plot starting in 2023 on the right, going to 2030. And we are already in a deficit for the cobalt supply. So one direction, let's say lithium-ion battery makers are going, is to go to chemistries that have lower and lower amounts of cobalt. But even so, counting that in, we are still going to have a supply deficit if we depend on our current sort of mining, refining supply chain. And thus this necessitates the sort of development of recycling technologies. And so this comes to our statement. Okay, so we say recycling is important, but our current recycling model is dysfunctional. So sort of in our little diagram on the top here, we can see the typical process where we start with mining and refining. You go to cathode manufacturing and battery manufacturing and then use. And sort of then we get to the end of life battery collection. And so in the United States, the end of life, let's say lithium-ion battery collection is in place logistically. However, for the most part, the only parts of the batteries that can be recycled are ones that have been before, like the plastic and the aluminum and the copper. Whereas, these really critical minerals are predominantly, if they're staying in the US, are going to a landfill. Or alternatively, we're selling them back to somewhere in China for re-refining. However, the current model is dysfunctional in terms of battery recycling because we do have issues with the safety of transport and storage of these lithium-ion batteries. And so this is we have what's called lithium-ion battery thermal runaway issues. I'm sure you've all traveled on a plane and they warn you about putting lithium-ion batteries into your luggage that goes into check-in, as well as what you're doing with your lithium-ion batteries once you're on the plane. And this is because most batteries have some charge unless they are full of energy, and if they are jostled or mechanically disturbed too strongly, they can discharge, which leads to a thermal runaway, which leads to fire. And so in the U.S., this is a big issue with, let's say, train transport, which can lead to a lot of mechanical perturbations, and is why you can no longer transport lithium-ion batteries by train. And so you can see in this image here, a lithium-ion, a train car that was started on fire by a lithium-ion battery transport. And sort of following this, I received an article just this morning on even the car manufacturers are having issues with electric vehicle battery fires. And so if the people who are manufacturing the vehicles are having issues, you can only imagine what the people who are dealing logistically with battery collection and transport in terms of end of life have to deal with, because they are definitely not the experts. Okay. And so this is where End Cycle comes in. Our idea is that we are going to disrupt the recycling market with sort of our innovative cost approach. And really one of the big innovations that we have is that our technology is modular, which means that we can be decentralized. And when you have a decentralized technology, you can sort of avoid a lot of these transportation issues. And so rather than building out one centralized facility, you can incorporate your technology in a modular format to wherever the batteries are being collected or pre-processed. And so this is what we sort of give you in this sort of circular chart on the right. If you look in the sort of upper left of the chart, you can see mining. Where we do have some, we're sort of getting into now some aspects where N-cycle could work with mining, but not yet. The mining goes to the refining, and again, the battery manufacturing application, and then the big yellow circle is the end of life. So as I said, we have a number of sort of logistical collection and mechanical separation facilities in the U.S. But at that point, they're only recycling the plastics and sort of the major metals to get out, the aluminum, the copper. But then the black mass, which is formed, which is this sort of has the active battery materials, the graphite, the cobalt, the nickel, lithium, incorporated into it, is typically sent to an offsite processing facility or a landfill, which is then going through classical hydro or pyro. Whereas rather than sending it to an offsite facility, we could install our N-cycle unit on site of the collection plant, process the materials there, and then send that off. So really, sort of the N-cycle disruption is in that we are modular and we can be installed on site of these logistical collection facilities. And sort of briefly getting into the electro extraction technology that we've developed. And this is a sort of a replacement. So what we've done is we've hybridized a few different classical, let's say, metal processing techniques. One of them being filtration. So typically, if you want to collect a material as a solid, you want to filter it. And then one common method that's always used in metal processing is electrowinning. So basically, taking a dissolved metal and converting it into a precipitated or a solid metal. And so we've hybridized a filter and this electrowinning process into one unit. So that's our electro extraction process, where we can do as a solution is flowing through our electrode, we can electrochemically precipitate the metal and then collect it on, and simultaneously collect it on the filter. And you can see the modularity in our device in that we are sort of generating these flat plates of electrode filters, which then can be placed in parallel in a single device, which you can see on the right, where we're taking our flat sheet and just putting, let's say, tens or hundreds of flat sheets in parallel into a single device. And then on top of sort of our disruptive modular sort of model, we've also compared ourselves to classical metal processing techniques. On the left is hydrometallurgy, and on the right is pyrometallurgy. So in hydrometallurgy, which first typically involves an acid digestion, so taking a metal or a metal mixture, dissolving it into an aqueous system, and then doing some sort of chemical precipitation or maybe a solvent extraction process, which are both very energy intensive to get the metals out, or pyrometallurgy, where you're typically heating your metals and melting them up to temperatures in the 1,000 degrees C range. Both of these have a high capex in that you typically have to build up massive facilities, and then the operating costs are also very high and also emit a lot of greenhouse gases. And so, we've put the N-cycle electrolyte extraction technology into a couple of cost models or energy models to compare to classical hydro and pyro. And in regard to the unit economics, the unit economics here being the operating cost in dollars to produce a kilogram of cobalt. What we've seen is for the N-cycle process, we get a 75% reduction in this operating cost, a 60% reduction in the total energy necessary. So this is in megajoules per kilogram of cobalt. And then a 75% reduction in the greenhouse gas emissions for N-cycle as compared to classical hydro and pyro. And really, this comes down to, we get numerous synergies by hybridizing what was classically or traditionally, unit processes such as filtration and electrowinning and metal precipitation into one singular and modular process, which can do all of these unit processes at once in a smaller, more compact single unit. And sort of going through just a general diagram of sort of our business model at this point. going from left to right, we first have the collected end of life, let's say batteries in this case, which then will go through a mechanical separation, which is typically some sort of shredding process, and then density separation, where we receive what we refer to as a black mass or a cobalt filter cake, which is a low percentage of cobalt and nickel. We would then install the N-cycle technology on site to upgrade this material to an added value cobalt nickel hydroxide product, where our initial sort of off-taker for this product would be refineries that could then take it and turn it into a battery grade cobalt or nickel. Alternatively, if we can we're doing some R&D to enhance our technology, the process, and then the other idea is if we could upgrade it ourselves directly to cobalt nickel lithium-ion battery cathode material. And really the business model would use a tolling agreement where we would just upgrade the material for cost. So to give you where we are today, I'm sure some of you who have been in the lab have seen the automated system we recently constructed, which is on the left. This is it can be monitored remotely, operated continuously. And then on the right, so we start with a mixed, let's say, cobalt, nickel, manganese, sort of leached solution. And then a couple of the products are what we can receive on the right, which is sort of the teal material is a mixed cobalt nickel hydroxide. And then the right, the black material is a manganese oxide powder. And these would be the materials that we would send off to the refineries for further processing. And sort of where we're at today is we just received our seed round of funding, and we'll soon receive our NSF phase 2. We have a couple of grants in place. And so really what we're looking at now is for the next 6 to 9 months is putting together our first customer pilot. And then the next stage would be to build pilots for our next customers. And sort of this is just a brief pipeline of what we're looking into in terms of our customers and partners and competitors. And so we've talked to a wide range of people in sort of both the battery recycling and mineral refining space. And then finally, looking at our team today, we have Megan, our CEO, up on the right, and then myself, Emily and Christoph and Sean, who are, I believe, all on this call. Emily, our mechanical engineer, Christoph, our director of product, and Sean, our VP of operations. And then a couple of our newer hires in the bottom, Danny, who's a business analyst, and Stacy, our office manager. But we are currently hiring. So if you know anyone who wants to come and work on battery recycling or a clean energy future, let us know. And then just a few of our advisors, Desiree, our co-founder, and then our John and John, our advisors from Tennessee. So I'll stop there and let me know if you have any questions.
Okay, as of right now, no one's put anything into the chat, so you can certainly raise your hand and just jump in if you so choose. Well, why don't I start off, Chad, by asking you a question. I noticed your filter frame. You said something about them being carbon or something like that.
Yep.
The filter frames, how durable are they? How long do they last? Do they have to be carbon? You know, those kind of questions. Why do you do that?
All right. So so that's a good question. So the filter lifetime is a very important question. Right now, we are up to about 50 hours of lifetime, but that really has been limited by how long we can test them for. So which is one of the reasons we put together this automated unit. So previously, to get to 50 hours, we had to do 10 days of 5 hours. And so now we are hoping that we can run continuously to get there much quicker. But 50 hours was our goal for lifetime, such that we could get a profitable unit margin. We are hoping to extend this even further, since the filters, the replacement of the filters at 50 hours is still one of our major operating costs. And for example, if we can get that up to 200 hours, that would greatly decrease our process.
What do you do with the filters when you're done with them? I mean, obviously you're trying to get a circular process going here. Do they go to landfill? Do they get burned? Can they be reused?
Yeah, we have not decided on that yet. One idea would be to try and regenerate them. So the major issue is, right, we are depositing or filtering out metals onto the filter. And so eventually that builds up. We can get some of it off with various hydrodynamic techniques, doing backwashing or turbulent techniques. But some of it just doesn't go away. And so we're thinking maybe we could do a post-processing, let's say with an acid wash, to regenerate the filter such that we could use it again. No, the other idea is if we can get it to operate for long enough, then do you just decide that, well, then we're just going to say it's going to be a sacrifice, say it's disposable, depending on what further processing it's going to, you can just go into that process and see what happens there. So we haven't quite figured out what that
There's
solution
still
is.
some work to do
There
there.
might be some options there as well.
Yeah. Okay. Bill Clary has a question for you. What other metals can be recovered with this process?
So we can do a range. So I've talked about today some rare earths, and then cobalt, nickel. But let's see, what else have we looked into? We've looked into a few of, let's say, sort of like the noble or precious metals, so like copper, silver, gold. We've also looked into some ores that are iron and titanium. So really, technically the process should work for most metals. The question really gets into how well can you separate those metals? So then they sort of fall into classes. And so, for example, it's really easy for us to separate copper from cobalt or the rare earths. And so it should be viable for a wide range. We've just focused on cobalt, nickel, and the rare earths because those were the ones with the biggest we saw as a need at the moment. And in the sort of the most open market, because with those metals, there really is no recycling today.
Yeah. Jim is asking, does your process recover lithium in addition to cobalt and manganese?
Yes, that's a good question. So lithium is one of the ones that we do not, are not able to collect with our process. But we have been in talks with a couple of companies. So the lithium just ends up in the effluent of our process, so the effluent water stream. And so we've been talking with a couple of companies about who are focused on lithium, battery grade lithium production, of taking our effluent and testing out their process on the effluent of our system for lithium recovery.
Great. Tom Ohl is asking where are the closest facilities that would use your equipment?
For the time being, most of the facilities that we've been talking to have been in Ohio. So in terms of a pilot scale device.
But that's really driven by where they are now. There's no intrinsic reason why they couldn't be more distributed across the country.
Yeah, no, that's it. Yeah, metal recycling seems to be located in Ohio. So, well, the major facilities today. So, but yeah, I mean, with our device being so modular, it's easy for us to go anywhere.
Good. Joel is interested in how water intensive the process is and how much water you need, and is that going to be an issue?
Yeah, so the water is a good question. And it's another one of those questions we'll get to down the road. Because really the idea would be, we're not doing it today, but to have the water essentially stay within the system until it's, so basically we would take the metals, we'll dissolve it into an aqueous solution, we'll put it through our process, then we'll take the effluent from our process, the aqueous effluent, and then use that to dissolve more metal. So basically you want to recycle as much of the water as possible within your system.
And then Tom again is asking a question about, is this a batch process or is it continuous, or where are you at in that progression?
So we run it as a single pass. So that would be, so a single pass. And so it is run as continuous. It's just that our continuity, is limited to a day. Well, now we have the automation system, so it can be longer. So we run it as a continuous flow system, not a recirculating batch process.
Chad, if I could add a couple more to that.
Yeah, sure.
So on the production level, full production level, it'll be a semi-continuous. Dissolution will probably be a batch process, but the actual electrochemical part of it will be continuous.
So at this point, and you have more questions, please either type them in or just unmute yourself and ask.
So, Chad, if you could talk a little bit about where this stands in the whole need for recycling and the, projected expansion of battery usage, whether it's for automobiles or electric storage. Where do you see your recycling device in answering the bigger issues that are sure to explode over the next 10 to 20 years?
Yeah, so at the moment, current place in time, even if you recycled everything, I don't think you'd have enough to sustain. That might be 20 years down the road. But for example, we've looked at one of the major battery collection facilities, and it goes through about 1,000 tons of batteries a year, and we could process that with what we estimate is 2 to 3 of these devices on the right, each of which takes up about 1,000 square feet. It's sort of, I guess it depends on where the recycling market goes, on how much we can, be involved. And on the other side, we've also looked at getting into mining because, a lithium-ion battery is, should have a lifetime of 10 years. So once it's out there for a while, and you're not getting it back, which is why we started looking into ore. And so there is cobalt ore in the US in a refinery in North America. The issue is the ore is too low grade, making the transportation to the refinery uneconomical. So one of the things that we've done some research and we'll soon start doing some actual experimentation on is looking into how we could try and upgrade the ore as well with our process, and thus sort of increasing domestic supply of sort of cobalt, and maybe even other materials as well with that. So I think there's a lot of opportunity. But not only us, but you're seeing a lot of people getting into this space as well because it's going to be so important.
Chad, this is an electrochemical process. So basically, the bulk or all of the energy is coming from electricity, yes, I assume. And I guess if you so choose, you can use renewable power for all that. So if essentially this can be almost no greenhouse gas at all, or is there some process or products in here that require you to generate some greenhouse gas?
So if you're talking about the device itself, it'll all be electricity, other than possibly the manufacturer of the materials. I don't know how detailed you want to go into all of the economics, but yeah. So when you're operating the system, it's pretty much electricity, and then some, then the chemical consumables, which is mostly in the pre-processing. So taking, let's say, the black mass and then converting that into a metal-containing liquid.
The reason I ask is there's been a lot of pushback from people who don't want to move to electric cars, for example, to claim that the processes to make and get rid of the batteries are intrinsically dirty, and therefore you're not actually being a good citizen getting an electric car. So I guess it sounds to me like the vast majority of the power you're using could potentially be from renewables.
Yeah, no, and that's sort of when we got into our unit economics, when we sort of compare ourselves to classical pyro and hydro for, let's say, production of these critical metals, we can see there's a large reduction in energy use and greenhouse gas emissions.
That's great.
And this is resulting from that we're not having to go, you can think about it is when you go to get a cobalt ore, it's 0.2% cobalt, whereas if you go and get recycled battery, it's 5 to 10%. And so just looking at it from that standpoint, the upgrade is less during recycling, and plus our process again has the synergies between the filtration and the electric chemistry.
We've got another question from Carol here saying, would the small batteries, including the little button ones, be worth the cost of recycling?
Yes. Well, you have to remember that like a Tesla battery is just 1,000 AA batteries, right? So it's not a huge difference between that and a button battery. So
Tom, question?
Go ahead.
Yeah, Chad, in many products, looking at the life cycle issues, does the government or government regulations play a role? I know with some products, they're requiring or suggesting that the original manufacturer take the product back at the end of its life. So with lithium-ion batteries, are either the battery manufacturers or the car manufacturers involved in this process?
So in terms of, let's say, government regulation, I think that's much further along in Europe than it is in the US. And I think in the US, the hope is that the battery manufacturers will take it upon themselves and see the value in recollection and recycling of the batteries, rather than having the government regulate that they do it. And there are a lot of these, the electric vehicle manufacturers are working with recycling companies at the moment, even just focused on their manufacturing scrap. So when they're making the batteries or they're making the cathodes, these companies, they lose 5–10% of that material. And that is a pretty low-hanging fruit in terms of recycling. So they're working on it. I don't know how far along they are, but hopefully they see the value in the recycling rather than going through the mining. And I think some of that is driven to by worries of these of dependence upon foreign entities for these materials. With the DRC, there is a lot of people concerned about artisanal mining, child labor, things of that nature. And then, obviously, with depending upon China for refinery. So there's worries there about just sort of more geopolitical issues. So, I think they understand the need for this. I mean, we've heard Elon Musk call for needing to get his own nickel supply. So, so that they're thinking about it.
That segues into Joel's question, which is how much of the economics of the process are based on rising prices of the metal? Can it work economically at today's prices, or is the government or manufacturer going to have to subsidize this? How does that work out now? Obviously, you're projecting from small scale, but
yeah. So it works today. The worry is, let's say if there was, geopolitical tension to rise, other countries could drive the price down. And that would be the issue. And then the government would likely have to step in. But cobalt and a number of the rare earths are all on the US government's critical mineral list, which means that they recognize these issues and the potential for a shortage of supply and the need for development of a domestic or North American supply chain.
is the government already, I mean, they're doing technology development grants, and obviously you're getting your phase 2, hopefully. But are there other things out there, other grants or programs coming out of the new initiatives yet? What's your view of that?
They are in the pipeline. It's just that when a new administration comes in, it takes 3 to 6 months for things to get restarted again. That's basically right. A new administration comes in, everything gets put in a bag, it gets shaken up, and then you have to start over. So we've been in talks with a number of governmental funding agencies, and they're just really trying to figure out, who's going to get what money and for what type of projects. And so they're sort of really in the organization, still in the logistical organization phase at this point, but it's coming soon.
You touched lightly on the competition. Obviously, a lot of people are working in this space. Do you see, are the alternatives out there primarily the same types of technologies? Are there other competing technologies you see that look promising? What do you see?
So the people who have made the most headway at this point have been on the logistical side, which is battery collection and then the mechanical separation, and maybe some transport type things. The ones that we are seeing coming out on the actual sort of black mass or that type recycling side all use classical sort of hydrometallurgic techniques. So basically what they're doing is they're taking, the classical hydrometallurgy that's been used for other metals and adapting it for use with these lithium-ion batteries. Have not seen a lot of new technology come out. So really it's people seeing that there's this emerging market and there's going to be a need. And so, just getting out there with sort of some more traditional type, techniques where we don't see a lot of people, like ourselves who are coming up with new technologies or emerging technologies and trying to use that sort of to reduce costs and reduce energy. So
it's great.
But there's definitely competition.
Well, that's good. We want to see this problem solved, and that's usually the best way to make it happen fast.
Yeah.
Any final questions? One last question, perhaps, and then we'll kick it back to Tom to wind us up. Chad, any final comments you'd like to make?
Nope, I just want to thank everybody for attending. Thanks for all the great questions and your interest in N-Cycle.
All right. Thank you very much, Chad, and the rest of your team. We wish you all the best of luck. And perhaps this summer or fall, I could come by for an in-person tour and see some of this fancy equipment. So best of luck to you. Thank you much. We have one more virtual presentation session lined up for the second Wednesday of June 9th. We have not confirmed the speaker and topic yet, but we should do that within the next week or so. So keep an eye out for that email notification and opening up of registration. And hopefully I'll see you folks online one more time before the summer weather gets here. It is going to come, right? It is going to be above 50 degrees one of these days. So thank you, Tom. Thank you, Debbie. Thank you, all the sustainability team, and thank you all for attending. We'll see you in June.
Sounds good. Thank you.
Thank you.
Thanks. Bye-bye.
Bye now. Thanks, everybody.